You're good. Thank you.
Oh, all right. Let's see. Josh is actually in the back, and Piotr in the back. I'm John Pleviak, in case you don't know me. I'm to blame for a great deal of the code in ATS. I wrote the host DB over like a weekend without any sleep. It should have been replaced many, many, many years ago. Yeah, so quick background. If you're trying to understand why it has that crazy multi-cache in there, that was actually the directory structure for the very first version of the cache that then got thrown away. And as a result, I just repurposed it because I needed something immediately, like last minute. Yeah, that's why it's there. Anywho, let's see. Okay, so I'm going to be talking about extending ATS with WebAssembly. So I know everybody likes Lua, but there are alternatives, and WebAssembly is, the new hotness, and so that's why we're going to talk about it. So the agenda is, first we're just going to talk about, WebAssembly and its use as proxy extensions, a little about the ABI, the API, the SDK, what the status of this thing is, and then I'm going to give a demo, which we'll see how that works out. So WebAssembly, in case you don't know, is portable sandbox machine code. It's a web standard, runs in all your browsers. There are good implementations available, including V8, let's see, Wasmtime, Wasmer, there's a bunch of them out there. And it has broad language support. In particular, C++ and Rust work really well. TypeScript works well. There's sort of a mini Go thing that works, and a bunch of other languages are in progress. It's fast. In particular, if you're using, say, V8 or WAVM, there are some large fraction of optimized C++. They run at like 60, 70%, so very close to native code performance. And it's safe, or at least relatively safe. The other nice things about it is it's portable, dynamically loadable, linkable. You can reload things. That's good. So what are the use cases we're looking at here? Well, one thing is to avoid making changes to the proxy proper. Another is that you can avoid restarts by doing dynamic reloading. I know that we can dynamically reload our plugins anyway, but you can also just dynamically reload the WASM code. Another nice thing is you can do canaries, A/B testing, and automatic rollbacks. You can do complex behavior because you're doing C++, and so you can pull in all kinds of libraries as compared to maybe Lua, where it's a little more difficult to do that. And you can do CPU-intensive things like transcoding, but you can do them in a plugin that's sandboxed, which is kind of nice. Yeah, it provides some isolation as well. So we've been working on this in the context of trying to provide a portable layer so that we can use these sorts of plugins portably between different proxies. So right now, we have the implementation on Envoy. We're looking at an implementation on ATS. It'd be nice to get into other things as well. And so we're trying to design an ABI and an API set that will embrace at least the majority of the features available on a number of different proxies. So the prototype for Envoy is in this repo here, and there's a proof of concept for ATS in my personal repo. And we'll be looking at that later. So the overall architecture looks like this. We've got, ATS has got a bunch of threads. Those threads would have individual VMs in them because we don't want to multi-thread the VMs. And then also we're going to have, or we'd like to have services, so singletons that exist to do things that are, global to the process. And then there's ways of sharing data, message queues and shared data so that you can have these individual threads and services talk to each other. And then the idea would be that you can push your configurations in, and maybe you've got some code repos somewhere, and you could dynamically load the code from that. using certificates and authentication, all that good stuff. Okay. So one decision we made up front was that because the threading standard isn't really, it's not standardized right now for WASM, and for performance reasons that each VM would be single threaded. And that makes things a lot easier. You don't have deadlocks and things like that. And also that we'd like to support multiple VMs per network thread. And if you're going to use this and you have a lot of plugins, there's some overhead to setting up each VM because there's a certain amount of memory involved. Currently, we support co-location of plugins in a single VM by linking them all together, and then we have a sort of virtualization process where you can say, there's a tag for each use case, and it will vector the calls into the VM to particular handlers that are tagged for that use case. In the future, when the standards come out for WebAssembly dynamic module loading, we would like to be able to just load multiple modules into the same VM, but right now you have to link it all in one place. So the proof of concept, though I'm going to show, it actually just has a single VM with using Big Lock technology because I didn't have a lot of time. Okay, so what type of things can you use this for? So we're looking at, services that can do like lifecycle stuff, monitoring. You can also do things like consolidating of statistics, maybe sending them in the background to Prometheus or whatever. Obviously, the remap APIs and HTTP, but we also want to do like, layer 4 stuff, and then whatever anybody else is interested in. So there's a couple layers of APIs, and one of them is the VM API. So the idea is that we want to allow multiple different runtimes to be used because different people have different use cases. And so one of the runtimes that we can use is the WAVM runtime. This is the one I use in the proof of concept. It's nice because it lets you do it ahead of time compilation of the WASM bytecode. The advantage of that is that you're not doing that on every one of your proxies. You can do that, in your control plane, and then just send the WASM binary across. It has a special user section in it that actually contains the compiled code. And then we also support V8 and another runtime, which we call the null sandbox, which essentially just lets you use the APIs that we have and compile directly into the proxy. And the advantage of that is that, say, it's an escape hatch, you can use any of the standard C++ calls at that point as well. But it also lets you put it under debugger, get your code working before you then just recompile it to WASM and then load it that way. And it's really easy to add a new VM. We've got nice little API. You just need to know how to register callbacks, get functions out of the WASM code, load, link, and start the thing, and then just copy memory in and out. So right now, the memory management we have is just copy in and copy out. It's simple, but it's not particularly efficient. And if you're doing something like transcoding, it may not be the best way to go. One of the issues is that the shared, I think it's called shared buffer implementations for WASM, it got disabled a while back. There's some security issues. We'd love to use that again once it becomes really stable, but for now there's a little bit of a limitation there. Let's see. Yeah, so the VM trade-offs, I talked about them before. What are they good for? WAVM has this pre-compilation. V8's got a lot of miles on it. Then also X is good for development and debugging. And then, what happens when something goes wrong? So we have some isolation. We can catch seg faults inside the VM, and then, you have set up a policy. When you load the code, what are you going to do? Fail open, fail closed. It's up to you. You could also roll back to a previous version or whatever. Okay. So for the ABI, which is the sort of low-level interface, we wanted to make sure we could support a bunch of different languages. So it's basically a very low-level C API. And then on top of that, for each different language, we have a whole SDK that then converts that into a language-appropriate interface that's much more high-level, much more programmer-friendly. So for the ABI, we want to have, something that has standard name prefixing. It allows for expansion to different prefixes when you've got, special code that only, say, ATS can run. It returns standard result codes. Data is passed out by pointer. It's passed in by malloc-ing something inside the VM and then copying data into it. And so everything is kind of standardized around that model. So in addition to supporting, things like the call-ins for when the headers arrive and calls to say, go get a header or change a header. We also support a bunch of standard APIs like events, metadata, getting generic configuration information, HTTP fetch, logging, stats, shared data, and message queues. And so here's an example of what the code looks like. So in proxy WASM externs, which is the ABI external functions, you'd have something like extern C, it returns a proxy result. The functions like get current time in nanoseconds. And since it always returns a proxy result, in this case, it passes in a pointer to the location it wants you to dump the value into. And then the ABI implementation uses a generic word result because you can have WASM 32 or you can have a native compilation in a 64-bit environment, and so we have an abstraction for a word, which is going to be the word appropriate for whatever the runtime environment is, and then it has a context that tells you what stream or what calling environment this thing is associated with. And then the implementation is going to basically unwrap all of these generic words, which may point to memory addresses inside the VM, and verify that those addresses are all correct, and then call the actual implementation, which in this case is going to be a function on the context. So the context, again, in this case, is whatever bits of information relate to this particular request that invoked this call. So it would be the state machine, the request structures, etc. And then finally, the context actually implements, in this case, with TS HR time. That's basically how you add a new ABI function. And so an example of the difference between the low-level ABI and the high-level API would be like stats. So the low-level one has something like proxy defined metric, and you hand in a name, and it returns you, and a type, and it returns you a token that you can use to access it, and then you pass that token back in to increment it. But at the high level, you want to do something a little more interesting. And so in this case, you can say, oh, hey, I've got my C++ counter. It has a bunch of tag types. I can then increment them by passing in the different tags, and it will cobble together the string, register the metric. You can also do a resolve. So you can resolve a bunch of tags to get a specific metric that then is registered, so then you don't have to keep going back to the system. This is much more efficient. This piece down here, which just increments this resolve metric, ends up corresponding directly to a single call to the proxy increment metric with the registered ID and the offset. So it's kind of, this API thing. Okay, so this is what it looks like to build a WASM plugin for C++ for HTTP. So you have a context that represents the particular request. So we can have lots and lots of requests in flight in any VM. And then you overload the functions that you're interested in. In this case, it's just the on-request header. So when request headers comes in, I want to do something. What am I going to do? Well, I'm going to log that I got called. I'm going to get the host header, and then I'll log that host header. I'll add a request header, and then I'll just return. And then you have to register this object with the system to tell it that this is the one that you want to use. And this registration thing also allows you to provide that tag I was talking about, so that if you've got 5 different plugins in the same WASM module, you can then associate it with the various places that you're plugging into. And that way you can amortize the cost of having this, spinning up this VM, because there's going to have to be a VM per thread.
So in contrast to the Lewis stuff, you're assuming a very little state inside the VM, right? All the data should come in, it should be processed, and then come back out. So it's very computationally oriented model.
Yeah. So instead of having say like a proxy object inside the VM that then behind the scenes makes calls, this model is more performance transparent. You ask for data, right? So like you would ask for all the headers, then you'd walk through them internally inside the VM. You'd make the decision about how you'd like to update them, and then you'd call out to update them, for example. So you don't just say, oh, hey, give me the header object, and then it kind of does everything behind the scenes. In this case, you have it's a lower level API. Yeah, so one of the things that I think we talked about this a little earlier, one of the sort of use cases that would be nice to be able to fulfill is, caching of control data. So when you want to do routing, you want to have the request come in, you want to get the headers, you want to check to see like if there's an outstanding operation with respect to this particular routing rule, and you want to queue yourself in the VM. If you found the VM is already send a request about this routing rule, you want to check the shared cache to see if it was populated with the routing rule resolution. You want to populate your local cache within the VM so that you don't have to keep going to the shared data structure with the locks. And if all else fails, then you make a remote request and put yourself in the queue. And then on the response, you can then fill the shared cache. You can wake up each waiter and restart all those operations. And we have APIs for that. There's a special call called set effective context, which says, hey, I've gotten this response. I'm going to pick this context, these waiting contexts, waiting operations, and now every time I make a call, like continue or change headers, I'm doing it for that particular request, and that way you can fan out the results of a remote call that has given you routing information to all the waiting requests, and get everything going again. So that's the kind of thing that we'd like to make possible, so that you can load this WASM plugin and then use it as a cache for like remote operations and things like this. But do it flexibly, because you can reload the plugin also if you want to change the plugin logic. Okay, so in terms of the SDK, we've got a Docker image that with the C++ development environment does scripting. It's got Absol if you like that, protobufs if you like that. The WAVM code in there, so you can do things like the ahead of time compilation I was talking about. It'll also disassemble things, so you can see what got generated. Yeah, you can also install the SDK natively. That works fine. And Rust has native support for WASM 32, but we still need to do some work on the SDK. It's basically all it can do is log stuff right now, so it's kind of vestigial. Okay, now the fun part, the demo. Let's see if we can get this to work. That's not where we want to go. That's where we want to go. Okay.
Here's the microphone.
Yeah, let's see if we can get this going. All right. Yes, if anybody has any questions too, you can just
we go. So I'd assume that I probably missed this, but I'm assuming that there's some glue layer between traffic server C APIs to WASM. So you have to like define all of that. How does that work?
Yeah, so that the thing I showed you about that getting the time in milliseconds,
Yep.
that's what you have to write in order to do the glue.
Okay, and then you have to do that for every language?
Oh, no, you just do that once because that's at the ABI level.
Okay.
And then there's a little bit of glue in the SDK, right? If you want to use it, like that whole class thing with the context, right? That is the part of the C++ ABI.
Okay.
Or API, right? And then it has support logic in there in C++ that converts from the low-level C calls to nice C++ stuff, right? So like normally when you make a call out, you get back a raw pointer and a size of a data object, right? You know, but it would be untyped. But that's the C interface, right? But the C++ interface knows what it expects. It converts it into a smart pointer, right? Because it's like, oh, I know this thing needs to be deleted, and I don't want to leak memory. And it puts, it types it and does all that good stuff for you.
Okay.
Yeah, and that's like per language.
Okay.
But implementing the ABI, you just do that once for inside traffic server, once for all the languages.
Okay. Okay.
Okay, so here we go. Let's see if I can get this going. So we already looked at the example, but so I'm just going to show you what the code looks like when it runs first. So this is traffic server 10.0. This is the on-start call gets called when the VM loads. So as soon as your code, your WASM code loads, it calls on start, and that gives you the opportunity to do anything that you want to do to sort of initialize the VM from your perspective. And I just put a log in there, and now I'm going to run some load through it. Okay, so we got JTest running, yay. -X just dumps all the headers. C1 is just one connection, and -E1 is 1 per second. And so we hit that. And as you can see, it's printing a bunch of junk out. So I'll stop it now, maybe. Okay. So it's printing out the headers. So if you look up here, you can see. Yeah. So if you look up here, it says on response headers, 9 is just the ID for the connection. And then it's like, how many headers did you get? Well, you got 2. You got proxy connection, keep live. Host is this Istio thing. Then you've got the response headers. You got 5 of those, and it lists those out. And then you get called back when you're done. And when you're, this is done is when the last byte goes through, and then delete is when you get deleted, right? So if there's sometimes there's another entry point here, like on log, which is like, okay, I've already sent everything, right? But now I want to log, so then you get on done, and then you get on log, and then you get on delete, for example. In this case, the delete thing is the context on the ATS side, which represents all of the resources that you might have, stored up that you allocated, for example, in traffic server in order to manage this thing. We're going to store those inside the context on the outside the sandbox, right? And then within the sandbox, you have another context that then represents that transaction, that request handler, right? Yeah. So you got a state that's for the request, but in this case, we've got one in both places, and so that's what's getting deleted here. And then if you look at let's see, the response from the proxy down here, you'll see that it has a new header, X WASM response, ATS WASM, that we added. So this it's not coming from the server. JTest doesn't send that natively, but this was added. Okay, and so I'll show you all the various bits of code. All right, the hardest part of implementing this was getting the configure system to understand how to load up the WAVM library, because I hate configure, and M4 and I are ancient enemies. We do not get along. All right, so let's see. Plugins, experimental, WASM. All right, I'm going to show you. Let's see. Okay, so this is, let's kill this one. Yeah, all right. So these are the files that you need to get this thing running. So basically, in this case, you have a make file that runs inside the Docker, and you've got a script that runs inside Docker, and then you got a script that runs outside, and then you have the code. So in this case, the code looks like this. It's just the example context. There's a root context, which represents the plugin. It represents an instance of a plugin running in this VM. Like I said, you could multiplex them into a single VM. And then that does the on start. And then there's a context, which represents the transaction. In this case, it only knows how to do like on request headers, on response headers, done and delete. And then you register it. The on start just, echoes back logs on start. On request headers, does what we saw over there. It prints out all the headers, and then it adds the request header, which is the, X WASM request with the ATS WASM. The response one, does something very, very similar. And done and delete just print. And that's the whole plugin right there. But we can change it. We can do anything we want with it. We could, say change, ATS to be like, 10, because this is version 10. If I could get my fingers to work. Yeah. And then, oh yeah, that might or might not have worked. Let's see. Unfortunately, I've got Clang format installed. It's the wrong version. ATS is still running on an old version. I'm running on 8, and the configure file is different, and so it complains every time I try to save anything with my autocomplete or my auto formatter. Okay, so then you can just to build it, you just say docker build cpp wasm, and if everything works out, it will run load up Docker, and it will run mscripten inside of there. Yeah, which it did. And then, in theory, let's see, we could rerun this sucker. I didn't implement the auto load or auto reload, sadly, but and now we run it again, and yeah, as you can see, it says ATS WASM-10. So it worked. The code is in my personal repo. It's, let's see, where is it? Experimental WASM. So it actually loads as, let's see, local user, local, etc. Traffic server, plugins. So it loads as an SO. So this is a plugin system that loads as a plugin, and then it loads the WASM code directly. I didn't make anything more complicated than that currently. But this is basically the code. So everything that starts with proxy WASM is part of the API or ABI. The only code that that we needed for this is the WAVM implementation, which is that wavm.cc file. The abstract API for VMs, which is the wasm_vm.cc. The loader, which is this WASM main thing. And then wasm.cc, which is the ABI implementation itself. And so if we look at this, let's see, it's not too big right now, mostly because I deleted a ton of code and only implemented the features that you saw there. So like those are the only ones implemented. And currently it's implemented on top of the C API, or the plugin C API. So if you look at it, it's like let's see, headers. I didn't implement even the ones that are like header pairs. What is it? So it would be like, let's see if we can find one. Oh, well, let's see. Okay, so for example, this is you'll recognize this. This is like the handler for the plugin events. And when you get the, TS event HTTP read request header, it then just calls my context. So for every time a request comes in, it creates an event, a continuation, and then that continuation, and it creates a context, local context, and then it associates those two, and so then when the TS event HTTP read request header comes in, it then makes a call in the context, which is the on request headers, that then calls into the VM's context with on request headers, and that's how the whole system just gets going. So that's basically it. Any questions? Sure.
So when you build this plugin, what other dependencies are there out there?
When you build the plugin, currently just the WAVM library, which you have to install on your machine in order to build this.
That's it?
Yeah, I mean, if we wanted to do V8, it would require V8 as well. Yeah, that and traffic server.
Right, yeah.
Yeah, that's the only two dependencies.
So when you're interfacing with a proxy server, you don't have to do just a C. Do you have to do just a C API? Could you use our C++ API?
Yeah, we could.
Yeah, that's what I thought. I was just double checking.
I used what was easiest for me at the time because I wanted to build this demo.
Yeah, our C++ API is just a wrapper around the C APIs anyway. So, but yeah, I was just kind of curious because we've talked about transitioning some of our C APIs to C++, but we've kind of held off because of this to see if we had to have C APIs as actually the kind of the interface into ATS or not.
Yeah, it was just the most convenient thing. There are more examples, and I was in a rush, so I was like, what am I going to do? Well, that's there.
Yeah.
Anybody else? Yes. Yeah. But the C one doesn't provide strong types, right? But they're all implied, right? So, it's in the description of the ABI, and then it's up to the language, whoever's doing the SDK for a particular language, to ensure that those things are all type safe on the other side.
So kind of continue what Brian asked before. Let's say I wanted to write one of these plugins in Rust.
Yeah.
What type of extra effort do we need to do in your plugin to get it to support Rust?
Nothing in the plugin, right? You just have to have a nice SDK. So the plugin, the way it works is that in traffic server, in the plugin that loads the VM, it's just handling C calls coming out and making C calls in. And then there's a little layer, shim layer inside the SDK for Rust that converts those into whatever Rust likes, right? So if we hand it some object, the way Rust works is we have to allocate the object. We have a call that we call into the VM, which is like, give me some memory. Then we blast whatever we're handing over to Rust into that memory, and then when we call in on the C call, it then wraps that in a safe Rust object and then hands it off to Rust in the manner that Rust likes things. So let me just show you what it looks like for C++. So there's let's see, the header maps. It's called pairs. Let's see. Yeah, okay. So header string pairs is just a vector of pairs of, string, kind of what you'd expect. There's also, a map. I think it's a map of like, string view to string view. So this is what C++ would do, but presumably Rust would do its own thing, right? It has its own native idea of what a string is, and it's going to have to convert the buffer that comes in. So the ABI says, hey, when I'm passing in or out a header, I marshal it in this way, right? I say, how many pairs do I have? I have the length of each pair, then I have the raw strings, and they're all in one buffer, right? So just blitz them in, and then it's up to the SDK implementer to decide what's natural from the from whatever the language's standpoint is, right?
Yes, I'm still confused. So that SDK, is that, it doesn't know about ATS at all? But how?
Yeah, the SDK doesn't need to know anything about ATS, so it just does conversion. So the basic like data structure, for instance, for C++ is this WASM data structure, right? So it takes a raw buffer, right, something that's just been handed to it by the C code in the ABI, and then it implements on it, like for instance, it can turn things into strings. It can hand you back pairs, which is how it hands back. Your headers, right? So your headers come in as a vector of pairs of string views into this buffer. And so that's, but from ATS's standpoint, all it's doing is implementing the ABI, right? It just takes the header and it either, if you ask for a single header, it just copies it into a piece of memory and then hands the C code that piece of memory, right?
So this SDK for us will be the same for ATS and for Envoy or anything else?
Right. Yeah. For all the things that it supports that are, ATS may have some special things that other proxies don't support, in which case they would have to extend the SDK. But to the extent that those things are common across proxies, then yes, the SDK would all be the same when we shared. And so one of the things we're trying to do is make that SDK, generic for all proxies.
And that's something you guys are maintaining, or is that sort of a community?
Well, right now we're maintaining the C++ one, right? And
Okay.
we have interest. So there's people who are interested in doing, Go and Rust, right? Or mini Go, I guess it's called, right? The one that doesn't have the garbage collection. But if there's some language that somebody wants that's supported by WASM that we're not going to support because we don't ever use it, then they presumably have to support it themselves. Get a community together for that. But yeah,
I guess kind of what I'm getting at, it would be nice to have some hard. I mean, we're not going to get our operations guys to write this type of C++ code, right? So for them to let's do something basic like today, they would do add, remove headers, whatever it might be,
Yeah.
do some filtering and stuff. We need a higher level language that
well,
can
that's
compile
what
into
it. Yeah, I mean higher than
C++.
higher than C++. But I mean, this is what the
Right,
code looks like.
like TypeScript, right? So,
But yeah, I mean, you could use TypeScript, right?
and is there an SDK for TypeScript? Is someone going to do that, or do we need to do that?
Well, I'm not writing a TypeScript one because I don't even like TypeScript. And I'm a C++ guy. But I mean, that's not that low level. I mean, that's like you just say, give me all my headers, right? Get request header pairs. You loop over them. You can print them out. If you use auto a lot, it could be anything. Just sprinkle it around.
What do you think, Miles? Are you going to write this?
I can't write that.
Yeah. Yeah, if you think Rust is higher level, then great, that's good. I mean, presumably you could run Python too. You could just, Yeah, you could do that. I mean, if you like untyped things, I think TypeScript is probably a better plan.
Right. I guess the better question is, we talked about it a little bit before. So
Yeah.
the community around this, would be open to to someone implementing, say, this TypeScript SDK, right? So we get it
Oh yeah.
part of a community.
Yeah.
And
I would certainly be super happy if somebody wrote that.
Well, let me see if I understand. So basically, the WebAssembly has a abstract virtual machine that represents the proxy. So what we'd be responsible for is writing something that mapped from that virtual proxy VM to traffic server. We'd write that once. Once you do that, then all the other languages work.
as long as they have an SDK.
Right. As long
Well,
as,
but their SDK is independent of traffic server. They're writing an SDK to the virtual proxy VM. Is that roughly correct?
yeah, that's the idea. That's the idea. Right. So that way you can amortize the cost of building these SDKs, and you can get language enthusiasts, right? If you're really hot on whatever, language is hot this week, then you can do it. Yeah. They're pragmatic.
So the question is why those VMs are not like something like Lucet or Wasmer that already implement the bindings for multiple languages.
Yeah, so I think it's going to be really easy to do like Lucid because it uses the standard API. So the C API was like maybe Piotr can come up here and help me with this. The C API was like kind of not a big thing when we started this thing out. It wasn't like complete, and certainly V8 didn't support it, right? And so when I was starting out, I was like, well, I know that all these like Bitcoin type projects are using WAVM, right? So I knew I could find an example of somebody embedding it, right? And so I was like, okay, I'm just gonna go find that code. And so that's when I glommed onto WAVM. And then of course we're Google, so we're like, oh wow, we can get V8 in here too, right? There's no reason to exclude another one. It was just happenstance, right? It's like what was convenient at the time. Right. Yeah. I think a lot of it is that you can pull in, for C++ in particular, you can pull in a bunch of external libraries. That's like a big win. Yeah, and it's also if you're a certain language house, like your C++ house, or you want to do Rust or whatever, that's the other big advantage, because maybe learning Lua is just not your thing today, right? Even though it would work, right? It's just like, well, but we already know this other language, and even though it's not better suited to the problem, right, we know it. So I think there's some advantage there as well.
Do you have any plan to implement some kind of resource constraints? Like, how do you prevent like wasn't planning to run forever? Yeah,
so in terms of memory, you can constrain memory, so that's not a big deal. But the running forever thing, we have plans and a design doc, although we have no implementation yet, for going in and instrumenting the code. So you can just do, I think it's like Kimona or something. There's a project that lets you do rewrite of WASM code, and you can go in and just annotate the call graph with counters, and then you just throw an exception out. Right, I know, or exit out or whatever. Right, it's like you can get out of there, and then you can either fail close or fail open, whatever you've configured the thing for.
Well, yeah, I mean that's a very like black or white case, right?
Yeah,
it would be more like, well, I want certain plugins to just take CPU for like 5 milliseconds or 10 milliseconds. or whatever.
Yeah, I mean, it's, with some support, you could do a little better if you trusted the person. Like you could, the SDK could, for instance, we don't have it working yet because there's some problems with Inscription. But in theory, the SDK could wrap your code in a try block, catch that exception, and then exit cleanly, right? It is also possible to just if you knew that this exception was one that you could just clear the stack and recover from, you can do that as well. But I mean, in general, we don't know that, right? Yeah.
This example plugin that you showed here, that will work equally the same on Envoy? Or
Yeah, that's actually the same one I use on Envoy. It's the same code. I mean, that's my example from Envoy. I'm really lazy, so I just copy the code. Yeah. I think you could do it. I think the limitation, if right now is you have to copy in and copy out of your data, but the shared buffer thing it's gonna happen, right? I mean, the community really wants it, so. Yeah, there's some complexity right now with Inscription in terms of, it doesn't support all the random syscalls. So, for example, annoyingly enough, Google's Absol library, if you try to use certain types of container classes, has this crazy histogram thing built in, which also wants to make syscalls at random, right? It's unrelated, but because it was all built for the Google 3 environment, which is a standard environment, they're like, yeah, why not throw it in? Now, it turns out that the STL doesn't really have those problems because they're not assuming that they're in a full-blown Linux environment. So, when you include libraries, as long as the library is self-contained, it's not a problem. Yeah, and another nice thing that's happening, and currently we're doing Inscription, but at least for C++, I think we're going to move to WASI, and I think when that gets standardized, we're going to start seeing a lot more WASI targets for libraries, right? Because people will be looking at doing things like this. So I think it's only going to improve in the future. All right. Anything else? Okay.